All right. Good morning, class. You are watching this video because you obviously got my email and it linked to this YouTube video. Um, so anyway, today, before I start this, you may want to go back to your email and print out the attachment that I sent with it. It's this file that has a couple of examples in it, and then I'll get this set up so that you guys can just write along with me as I'm going through this problem. So when we get to this section on, it's called hypothesis testing. It's another branch of inference, just like confidence intervals are part of inference where we're making a conjecture about a population parameter. And with a confidence interval, we're trying to estimate that. And when the hypothesis test, we are trying to test to see if a claim has merit or not. And I've got two examples of that here that I want to go through with you today. And then we're going to continue with this on Thursday. So what I get through today should probably get you prepared to take the practice quiz that'll be due again on Wednesday night, tomorrow night at midnight. And then I'll wrap up the rest of the stuff and cover a few more things on Thursday in class. All right, so bear with me. I'm hoping that my cough will hold off until we get to the end of this. So here's a typical problem. The machine is used to fill up water bottles. It's designed to fill them with 500 milliliters of water. Due to natural variation in the filling process, the engineer considers the machine to be operating correctly if the bottles are filled with a mean of 500, but then there's a standard deviation of 4.5 milliliters. So there's going to be some natural variation from one bottle to the next. All right, and then we're also going to assume that the distribution of fills is approximately normal. So a quality control engineer is concerned that the machine is underfilling the bottles. He takes a simple random sample of 10 recently filled by the machine and finds the mean to be 497.5. Okay, assume the standard deviation remains 4.5. Does this sample provide sufficient evidence to suggest that the mean amount of water for all bottles filled by this machine is less than 500? All right, so let me start this off by saying we've been halfway through a statistics class, and we are probably smart enough to know that if we look at this, this is the claim that the mean is 500. We got a sample mean of 497.5. Somebody that doesn't know much about stats would say 497.5 is less than 500. I'm done. Okay, this machine is excuse me, is underfilling the bottles. Right. However, we know that there's going to be some natural variability from one fill to the next, and we might expect to see something like this from a machine that is actually performing the way it's supposed to. Okay, so I'm going to kind of walk through the logic on this and kind of fill in details as we go. But the logic on this is we're going to make an assumption. We're going to assume that the machine is working perfectly fine. And if the machine is working perfectly fine, that means that the mean amount of water in the bottles is 500. Right? We're trying to check to see if there is evidence to suggest that the mean is actually less than 500. All right, and I'm going to put here some good modeling, and that is to define what I mean by mu. All right, so mu is the mean amount of water dispensed by the machine. All right, and if we think about the population here, the population is every possible bottle that this machine could fill. All right, and we're saying that the mean is 500, and we're trying to check to see if there's evidence against that it's less than 500. All right, save yourself a little bit of room here, probably about that much room, and we're going to come back and fill in some details on that. Also, we're going to put something out here that we're going to define what these two statements are called. All right, so now we want to skip down to the mathematics part of this one and think about the sampling distribution of x bar. Okay, sampling distribution of x bar, we're going to say, is approximately normal. Right? And the reason I can say it's approximately normal is not that the sample size was more than 30, but because the population is known to be approximately normal. All right, so we're going to say that that's approximately normal. We're assuming that this is true, that the mean of x bar is 500. We're assuming that this is a true statement up here. All right, then the standard deviation of these fills is sigma divided by the square root of n, and sigma divided by the square root of n ends up being 4.5. Okay, divided by the square root of 10, and that's going to give me 1.423. All right. This is what we'd expect the sampling distribution to look like, provided that the machine is operating correctly. Okay, we got a sample mean of 497.5. That's over here someplace. Right, and really what we want to know is that a typical kind of observation from a machine that is working properly? Right, so in order to do that, we're going to calculate what is the probability that we're going to get a sample mean that is at least this far below 500. All right, so a couple things I'd like to do here. One is I would like to calculate the z-score for this. All right, I think it's important that we do a z-score for this as well. So 497.5 minus the mean, 500, divided by the standard error, the standard deviation, which is 4.5 divided by the square root of 10. All right, so this z-score, it looks like I didn't calculate that ahead of time, so bear with me. 497.5 minus 500 divided by 1.423. Okay, this z-score is negative 1.757. Okay, so that tells me that this 497.5 is about 1.75 standard deviations below the mean if the machine is operating correctly. So I want to know how unusual is that. So I want to calculate the probability of getting a sample mean that is less than 497.5. Okay, and you can also say this is the probability of getting a z-score that is less than negative 1.757. Okay, these two should give me the same number. All right, so when I calculate this probability, the probability that x bar is less than 497.5, this is just going to be a normal CDF. So the second bar is normal CDF. We're going from a lower bound. I can never find that EE 99, so I'm just going to say I'm going to put in negative 1,000. All right, that's going to act like negative infinity. We're going to go up to 497.5. We have an assumed mean of 500, and the standard deviation is 1.423. Oops. And we get this probability is about 3.9%. Okay, now that number is an important number for making my decision. All right, I want to back up and fill in a couple of details now before we proceed. And first thing is that this thing that we're assuming is called the null hypothesis. And you're going to see it abbreviated by H sub 0. Okay, it's just a claim that we think is possibly true. And then the other hypothesis is called the alternative hypothesis, HA. Sometimes you'll see this called H0, and some books will call this H1. All right, so what we'd like to be able to do then is think about, what do we think about these two claims? Do I think this is true, or do I think maybe this is true? All right, another detail that I want to fill in here is the conditions that allow me to get from here down to the sampling distribution, and there's a normality. There's a normality condition that we need to check, and we're going to say that the distribution of x bar is approximately normal. because the population is approximately normal. Okay? Now, if we weren't given that information, we would have to probably need a bigger sample size. Okay, we'd need 30 or more. All right, then the other condition is the random check. Okay, so in this particular case, I need to make sure that this was a random sample, and it says here he took a simple random sample of 10 bottles. So I'm just going to say stated in the stem. Okay, so typically when I look at your work on a hypothesis test, I'm going to say this is the first thing I'd like to see. I want to see the hypotheses, and I'd also like to see the parameter that we're trying to test, and just define what that is. Okay, the second step for a hypothesis test is the conditions that are necessary, or the assumptions that we're making. Okay, the third step is to use the sampling distribution to find out how unusual is it for us to get a sample mean, in this case, that was this far below 500. Okay, I'm going to refer to this as kind of mechanics. All right, now, the other thing is that this thing is called the p-value. Okay, the p-value of a hypothesis test. It's really just the probability of getting a sample mean that is as extreme as the one we got, and it's a conditional probability assuming that the null hypothesis is true. Okay, so now we have to make a decision. One thing we have to decide on is, do we think that this number is a big number or a small number? Okay, you can probably anticipate that if I was in class with you today, I would say, how many of you would say that 3.9% is a high probability? And how many of you think that 3.9% is a low probability? And I would guess that probably the people that vote for the low probability would win this one. Okay, so there's a low probability that this is going to happen, just due to chance. Okay, so what do we think about this 500? Do we think the machine is operating correctly? All right, this is the probability of getting a sample mean as far away from 500 as we got if the machine is working correctly. Okay, one of two things could explain why we got a small number here. One of those could be that he just happened to pick a sample that was, kind of low on the filling scale. Okay, that's one thing that could happen. All right, so this is not impossible. It could happen sometimes. Okay, the other thing that could happen is that this wouldn't be so unusual if the alternative was true. All right, so that's what we're going to look at. We're going to say, what do we think about the null and the alternative hypothesis? All right, so if we say that this p-value is a small number, we're going to say our decision is, number one, to reject the null hypothesis. Right? So the fourth step of a hypothesis test is the conclusion, okay, or the decision. All right, so my decision is I'm going to reject the null hypothesis. Okay? And I'm going to say because the p-value is small. Okay, on Thursday, I'm going to talk a little bit more about this. There may be some questions in the homework that say compared to the alpha level. All right, so the alpha level is just a line in the sand that says, all right, if the p-value is smaller than this number, then we reject the null hypothesis. We say that that line in the sand is where we say anything smaller than it is small, anything bigger than it is big. All right, so a lot of times you may see that the alpha level, by default, a lot of times is going to be 0.05. Okay, so if the alpha level is 0.05, we could say we're going to reject the null hypothesis because the p-value is small, or we could say the p-value was equal to 0.039, which is less than 0.05. Right? We're saying the same thing either way. This is just quantifying what do we mean by small. All right, so what I'm going to expect to see is a decision about the null hypothesis, a reason for making that decision, and then the third thing is I want to say this in layman's terms. Okay, so this is a nice template that you can use. I'm going to say we have sufficient evidence to suggest that machine is underfilling the bottles. Okay? And so the conclusion here is the quality control engineer should probably shut down the machine and recalibrate it. Okay? All right, so this is the process. And you're going to find that in the next couple of weeks, we're going to be looking at several different kinds of hypothesis tests. This number system of 4 parts to the hypothesis test is going to kind of follow for every single one of those different kinds of tests that we're going to be doing. Okay? All right, so I've got a second example. And this one I actually stole from my son. His name is Mike, and he studies bats. He's right now he's out on the coast of Florida capturing bats and tagging them and doing blood tests on them and stuff. And so I asked him, what kinds of bats are you talking about? And he told me that these were the kinds of bats. The big brown bats are the most popular ones, or the most common ones that they catch. Right? And so let's say that he's been studying these bats. There's been some large-scale bat studies, and the weights of the big brown bats in the United States are known to be approximately normal, with a mean of 175 and a standard deviation of 1.1 grams. All right, this is for adult bats. All right, so Mike is studying some brown bats in Mexico. Okay, he wants to determine if the mean weight of the bats in a particular Mexican colony is different than 17.5. All right, so are they different than the ones that are in the United States? He collects a random sample of 20 bats, weighs each one, and finds the mean weight to be 179 or 17.9. Okay, and again, if a person doesn't know much about statistics, they might say, well, 17.9 is different than 17.5. All right, we're smarter than that because we know that there's some variability in these weights as well, and we may or may not be surprised to see a sample mean that is this large or larger. Okay, does the sample provide sufficient evidence to suggest that the mean weight of all brown bats in the Mexican colony is different than 175? And then we're going to assume that sigma is 1.1 for the Mexican bats. And then also one other thing we're going to assume is that it also follows a normal distribution. Okay, so if we think about it, the first step is we want to put down some hypotheses. Right, so the null hypothesis and the alternative. Okay, so what we're going to assume is this colony of bats is no different than the ones in the United States, so we'll say mu is 17.5. All right, and then the alternative, I've underlined the word different a couple of times in this problem, which means we want to know, is the mean something different than 17.5? All right, and then let's define what we mean by mu. Mu is the mean weight of all bats in the Mexican colony. All right, and this colony that I'm talking about is like, maybe there's like 10,000 bats in the colony. It's a fairly large colony. All right, so there's the conditions. I'm sorry, the hypotheses. Now the conditions that need to be met is normality. Okay. For the normality on this one, again, we've got a sample size of only 20, right? But we're told that the distribution is approximately normal. So the distribution of weights of the Mexican bats is approximately normal. All right, and again, if we weren't given that information, we would need to have a bigger sample size. We need to have at least 30. All right, and then also the randomness. Okay, I think it's set up here that he took a simple random sample. So he collects a random sample. I'm going to assume that means a simple random sample. So I'm just going to say stated. Okay, this is important because maybe he only caught like the slowest bats. And if he was catching just the slowest bats, maybe those are the ones that are the heaviest bats. So we want to make sure that this is not introducing any kind of bias, and so that's why the randomness is an important component here. Sorry, I can't not stop coughing. I wish I could. All right, so the third step is the condition. So we want to look at the sampling distribution of x bar. All right, because the condition was met up above, we're going to say that this sampling distribution is approximately normal. And we're assuming that mu sub x bar is 17.5. The standard deviation of this sampling distribution is sigma divided by the square root of n. So in our case, that's 1.1 divided by the square root of 20. And this ends up giving me 0.246. All right, so this is what the sampling distribution looks like. Now we go back and we say, well, what did we get for a sample mean? We got a sample mean of 17.9. Right, so I'm going to go here to 17.9. And what I want to know is, how unusual is 17.9? Right, so I'm going to look at probability being out here in this tail. All right, so I'd like to calculate first the z-score for this. The z-score for this one is going to be our observed mean. I didn't write this on the other one. I should probably have written this down first. Okay, divided by this. All right, so our sample mean was 17.9. Our hypothesized mean is 17.5. Our standard deviation was 1.1, and our sample size was 20. All right, so this gives me a z-score of 1.626. All right. Now, I want to calculate this probability, but there's something else that I need to look at up here as well. All right, so on our last problem with the filling of the bottles, our sign up here was less than. Okay, now it's not equal to. If this sign up here said greater than, all we'd have to do is calculate this probability, and we would be done. All right, but this one says, is it different than 17.5? So what I want to think about is, look at this distance away from 17.5, all right, and we're looking for what's the probability of getting a sample mean that is at least that far away from 17.5. All right, now when I say that, I mean it could also happen in either direction. So if I think over here, 17.9 is here, that's a difference of 0.4. Right, so I would make the same decision if I was over here at like 17.1 or below. All right, so here's what we do. We're going to look at what's the probability. It's not the probability that x is not 17.5. It's the probability that we're going to be at least this far away from the mean. All right, so if I look at the probability of getting a z-score that is bigger than 1.626. Okay, now I calculated this probability ahead of time, and I'm going to tell you that that number was 0.052. All right, so if I want to know what's the probability of being this far above the mean, this probability is 0.052. The probability over here is also 0.52, or 5.2. All right, so when we do this is called a two-tailed test. We calculate the probability of being in one tail, and then we double it. Okay, so the p-value is equal to 2 times this, okay, which gives me a p-value of 10.4%. Okay, so now we need to make a decision. All right, so our decision is, what do we think about this null hypothesis? All right, so we have to, again, interpret, how about this 10.4%? All right, if I asked you, do you think that 10.4% is a high probability? Some of you would probably say yes, and some of you would say no. All right, so this is why we kind of use that line in the sand and say, let's use an alpha level of 0.05. All right, so any p-value that's bigger than 5%, we're going to say is a large probability. Anything that's less than 5%, we're going to say is a small probability. All right, I'm going to elaborate on that a little bit more on Thursday about why do we kind of default to 5%. All right, so with that in mind, we're going to say that this p-value is large. All right, if the p-value is large, that means that this 17.9 is not a really unusual observation. Okay, so it tells me that it's really quite possible to get a sample mean of 17.9 from a population whose mean is actually only 17.5. All right, so our decision here is we are going to, this is the third step, fourth step, we're going to say fail to reject the null hypothesis. Right, and this might sound kind of strange that we're going to say fail to reject rather than accept. Okay, now the problem with this is kind of like, do I really think that the average weight of all the bats in that colony is exactly 17.5? You know, I really don't think that it's exactly that number, but what we're looking for is evidence against it. So the way you can think about making this decision is kind of like in a court of law. When the judge hands down his decision, he never says, you know, I find you, well, he says either I find you guilty or I find you not guilty, right? And when we say that somebody is not guilty, that does not mean the same thing as they are innocent, right? So the same thing here. I'm not going to say I think that the mean is 17.5. I'm going to say I don't have enough evidence really to dispute that claim. All right, so that's why we say fail to reject rather than accept the null. We're going to fail to reject the null hypothesis, and we're going to say because the p-value is equal to 0.104, which is greater than 0.05. Okay, it's bigger than the alpha level. All right, so then my conclusion is going to sound a lot like the conclusion that I had for the water filling, and that is we do, and in this case we do not have sufficient evidence to suggest that the mean weight of all bats in the Mexican colony is different than 17.5 grams. Okay? All right, so this is an example of a two-tailed test. Other than it being a two-tailed test, the procedure is going to be very similar to what we did on the water bottle filling. Couple things to really pay attention to here is this, what we're looking at, has to be a population parameter. If I put X bar in here, that's really, really wrong. Because X bar, we already know what that is. The X bar is 17.9, and there's really no reason to do any kind of a condition here, or any kind of a hypothesis test here. These two things are important. The normality check allows me to use the central limit theorem. The randomness is important, that we don't have a biased sample. All right, the mechanics is a lot of the stuff that we've been doing lately has been calculating these probabilities, and so finding the p-value is just an application of that. We find the p-value, then once we find the p-value, I want to do three things. One is make a decision about the null hypothesis. I want to base it on the size of the p-value, and then I want to make a statement that is kind of in layman's terms. Okay, it has something to do with the context of the problem. All right, so again, I apologize for not being in class. I'm sure you're probably not all that disappointed, but I did want to make sure that we keep up on the schedule, and so I think that this video is going to serve that purpose. So you should be working on the practice quiz it'll be due Wednesday night, as usual. And then on Thursday, I want to go through a couple more of these hypothesis tests and talk a little bit more in detail about some of the things that we need to focus on a little bit about in terms of interpreting confidence, or not confidence intervals, but just the whole idea of doing a hypothesis test and how it fits into what we've been doing in class. All right, I will see you all on Thursday. Hopefully I will be much, much better by then. Have a good day, and I'll see you then. All right, bye.